Hello, and thank you for joining us. Today's webinar will be focused on some key GC applications seen in the lab. We will touch on PAC's rich analytical history, discuss different areas where you might encounter GC, and what to do when your needs fall outside of standard applications. I'm Nicole Locke, the Group Product Leader at PAC, covering the molecular and atomic products. I'm joined by my three colleagues, Mango, our applications specialist for Asia Pacific, Rob, our applications engineer for Europe, Middle East, and Africa. He also plays a key role in our global GC support, and Basu, our application specialist for the Americas. So a little bit about me. I've been in the analytical instrumentation industry for just over 17 years. Most of that time was spent focused on GC and GCMS as a field and headquarters service engineer, a marketing specialist, and a product manager. I like to tell everyone, if you can break it on GC or GCMS, I can fix it and recommend how to run it now and in the future. Now that you know me, here's a little about PAC. It's a synergy of long-established scientific companies with complementary technologies. Over the years, they've come together to serve the industry needs in both laboratory and process solutions. In the early 2000s, PAC acquired both Antec, known for their elemental solutions, including the SCD-NCD unit we've come to know as the Sense, and AC Analytical Controls, known for their innovative and robust applicated GC analyzers. Based in Rotterdam, Netherlands, AC Analytical Controls has been around since 1981. AC was born from a project need of a well-known industry player, and that tradition of working with collaborators to build instrumentation for the future continues over 40 years later. Here, we see an example of the evolution of our technologies with an original Piona instrument produced in 1987 on the left, and on the right, a brand new M4 reformulizer system. While the technology has changed, for example, from packed columns to capillary, the essence of GC remains the same. Regarding GC as a technique, it was developed in the 1940s and has been noted as being used in the petroleum and oil and gas industry since the 1950s. Early applications were performed with packed columns in an isothermal oven, with detection typically being done on a thermal conductivity detector. These applications typically took hours on end to achieve separation of the complex mixtures, but this helped pave the way for what we see now. In today's laboratories, speed and simplicity are what drives the future. Over the next hour, we will be honing our focus into 4 different applications that fit the needs of today's laboratories. Those applications are boiling point analysis using our simulated distillation solution, refinery gas analysis using our RGA with excellence reporting software, group type analysis using the M4 with pre-fractionation option, and custom system requests. Now I'd like to hand it off to Mango to discuss simulated distillation.
Thank you, Nicole. Before I start, let me do a quick introduction about myself. My name is Mango. I'm the application specialist for gas chromatography application in PAC to support technical inquiries and application issues that encountered by our customers. I hold a Bachelor of Science in Applied Chemistry from the University of Malaya and currently live in Singapore. Before joining the PAC team, I worked with Sesco Services in their Biological and Chemical Technology division as a chemist to do wastewater analysis using GCMS. I was also a research engineer under Chemical and Biomolecular Engineering Department in National University of Singapore, where I was responsible for the treatment of wastewater and biomass through the utilization of green technology. What is SIMDIS? Simulated distillation. Distillation is the most widely used separation process in petroleum industry. Usually, refineries require the boiling point information for quality control, for regulatory compliance, to have a better control on their process, and to know various product yield prediction. In conventional analysis technique, we make use of physical distillations by using distillation flask, condenser tube, collecting or receiving flask, and a heat source to do the physical distillations. So the SDM method is D86, which is the conventional physical distillation, and D1160, which is the vacuum distillation that gives us the average boiling point data. And in modern analysis technique, we have simulated distillation by using gas chromatography. We have this distillation tower in the refinery to separate different boiling point products. For example, refinery gas like naphtha, gasoline, kerosene, jet fuel, diesel, lube oil, and bitumen. In simulated distillation, the goal is to simulate the distillation towers to predict yields or measure the tower cuts. SIMDIS provide true boiling point data up to 750 degrees Celsius versus ASTM D1160 that can only go up to 550 degrees Celsius. SIMDIS also gives automation results in minimal operator involvement, unlike physical distillations. And SIMDIS has a superior reproducibility, technically 5 to 10 degrees Celsius, versus physical distillation with 10 to 30 degrees Celsius. And lastly, SIMDIS perform faster analysis, typically 2 to 45 minutes, versus for physical distillation, 30 minutes to 20 hours. What are the SIMDIS applications in refinery? As you can see from this diagram, these methods can be used for SIMDIS applications. For example, D7169 for residual testing, D7500, which is the lube oil analysis, and it is using the same hardware as D7169, and the more common one will be D2887 for diesel range analysis. And also we have some other methods in ISO and IP as well for SIMDIS applications. Why SIMDIS is important in refinery? Because it helps in optimizing the distillation cut point. You can imagine if you cut it too early, you might lose the valuable portion that go to the less valuable end products. In short, it can help to generate higher profit by providing accurate information to optimize the distillation cut point. How SIMDIS works? First, you will need to calibrate a system with N paraffin standard to determine the retention time. The boiling point temperature will be assigned to the time axis, and the boiling point calibration curve is created. This is to establish the correlation between retention time and its belonging boiling point temperature. And from this data, the boiling point range distributions is obtained. For boiling point calibrations, we'll use the known N-alkane series. So as I did mention in the previous slide, is to establish the correlation between retention time and the boiling point temperature. And it must cover the complete boiling point distribution range, meaning to say that it must contain at least one N-paraffin below and one N-paraffin above the sample range. The sample boiling point range must fall within the calibration range. Next, SIMDIS value proposition. One thing that can differentiate PAC SIMDIS with other brands is we have TPI, temperature programmable inlet. It is specially designed inlet for SIMDIS for best precision and accuracy. It has liner optimized for CS2. In simulated distillation analysis, the sample generally consists of higher boiling components in a very volatile and expensive solvent such as CS2 carbon disulfide. CS2 boiling point is 46 degrees Celsius, If we just use normal inlet with a high temperature, it might have evaporated before entering the column, and it will lead to poor sample integrity and inaccuracy of your result. Our proprietary TPI will slowly heat up from ambient to high temperature to allow light ends to evaporate first before the heavy, so that it will not cause overloading at the first place and prevent sample discrimination issue. You will require lower maintenance with longer column lifetime. Next, we also have this septum purge line feature to work with our TPI. Baseline is very critical in SIMDIS application as it will affect the result directly, where a sample area will be subtracted by your blank. And we found that this additional septum purge feature to sweep away the leftover components under the septum can significantly improve the baseline performance and ensure a better accuracy of the result. You can see from the table, we perform better than what method has requested. Difference of boiling point found is less than 2 degrees Celsius compared to the difference of boiling point allowed. In short, septum purge line can ensure we can get a very decent baseline and give us the best result accuracy. Apart from that, we have this light solvent optimized ALS. You can see the temperature profile of ALS tower sample tray. It is easily to go above 50 degrees Celsius during the analysis. For your information, boiling point of CS2 is 46.3 degrees Celsius. If this is the diluted sample with CS2 solvent, when you place the vial on a tray that is higher than 50 degrees Celsius, it might lead to losses of your sample, especially the light ends components. With this light solvent optimized feature, with a modified inlet fan that is hidden in the GC, it can help to lower the temperature of the sample tray so that it is lower than the boiling point of CS2. It can help to ensure sample integrity to reduce losses due to evaporations of the sample. Besides, we do provide calibrations and QC samples. These are ILS-based certified consensus value, will be included in all analyzers with MSDS, certificates, or the analysis results. Last but not least is our SIMDIS Excellence software. It provides multi-language support. Currently, we have 7 different languages available, but other language is also possible upon request. In SIMDIS Excellence software, you can always set your calibrations as your primary calibration, so it can apply to your every sample run, or just with an easy drag and drop, drag the correct calibration and drop it to your sample so that you can apply any calibration to your sample to do the calculation and generating the report. You may create different product configurations, for example, crude, diesel, or some other product types to run the analysis. It is flexible in terms of reporting. We have the reporting template, and at the same time, you can also choose your preferred reporting parameter. In SIMDIS Excellence software, we have all key calculations and correlations needed. For example, recovery, cut point, distillation correlations to D86, D1160, calculated flash point, and some other correlations calculations as well. Lastly, let's do a quick recap on the SIMDIS topic that we went through just now. SIMDIS is a critical analysis for refinery. It provides high return on investment. We have TPI with septum purge feature to ensure your sample integrity. We also have this light solvent optimized ALS to prevent sample loss, and also the versatile use of SIMDIS Excellence software that is easy to use and flexible enough for your routine analysis. Next, I will hand it to Rob to discuss further on refinery gas analysis.
Thank you, Mango, for all the insights on simulated distillation. And hi, I am Rob Strick and have a long history working for PAC, currently in the role of application support engineer, and today My part of this presentation is about refinery gas analysis. When we look at the gases found in the hydrocarbon processing industry, we can distinguish them into natural gas, LPG, condensates, petrochemical feedstocks like ethylene and propylene, and the topic I will discuss today, refinery gases. Refinery gases is a collective name for all the gases that can be present in a refinery or other petrochemical plants where the gas composition is or can be measured. The composition of these gases can vary greatly depending on where the gas has been sampled in a refinery. As an example, the gases at the atmospheric tower of a refinery contains mostly methane, ethane, etc. The gases from a hydrotreating process contains typically high concentrations of hydrogen. So why would one measure the composition of these gases? Logically, for process control, to be sure that various processes in the plant are in check, optimized and efficient. For environmental reasons, for example the composition measurement of the exhaust gases. And lastly, from the composition one can calculate the energy content of a gas, which is useful information when it is used as a fuel at a furnace, which represents a certain value. PAC offers the high-speed RGA-GC application that can determine the composition of this broad sample scope in a short time with excellent performance and compliancy of the various methods available on the market. The GC application consists of 3 channels, where at each channel the entire gas is introduced by a gas sampling valve with a sample loop. One channel determines helium and hydrogen detection by TCD. The second channel separates the hydrocarbons on the plot column using the FID for detection. And the third channel is used to determine oxygen, nitrogen, carbon monoxide, carbon dioxide, and hydrogen sulfide by TCD. The 3 channels run simultaneously, but can be configured to run individually. This setup produces the 3 chromatograms we see on this slide, all run in parallel, which in the end results into one final report of the composition and potential other calculations like the calorific value that is calculated from the gas composition. The GC application does all this, of course, with excellent performance and repeatability, as can be seen here in this graph, where we see the area repeatability of the various components in the gas. In addition, the application is in compliance with a large variance of methods as listed in this table. When we need to describe what is important for the operator and robustness of a refinery gas analyzer, we can highlight these 4 listed features. Having a shut-off valve for repeatability, the use of robust inert materials, automated regeneration of a 13x column, and an operator-friendly software, which I will highlight in the next slides. To start with ambient pressure injection. This is of high importance if one wants to analyze samples with repeatable results. Practically, we are injecting a fixed volume of gas via a loop. To be repeatable, one must always introduce the same amount of gas. The amount of gas introduced is based on the ideal gas law we see here on this slide, and is dependent on 3 factors. The first is volume, which represents the size of the sample loop, which is constant. The second is the temperature of the gas. The gas sampling valve and loop are mounted in an isothermal heated valve box, and because of this, the temperature is constant for each analysis. Lastly, we have pressure, and this is the only parameter that can vary between analyses. so you must take care of this to be repeatable. In general, gas is introduced at atmospheric pressure. By adding a sample shutoff valve, we remove the operator variance in opening, flushing and closing of a gas sample cylinder and the time in between the operator starts the analysis on the GC. The pressure in the loop may not yet be at atmospheric pressure at the moment of injection. In our setup, the operator only needs to open the cylinder, set a good flow, and wait for 30 to 60 seconds and start the run. Once started, the valve will close the sample flow, allowing the pressure in the sample loop to drop to atmospheric pressure, and at a fixed time, the gas sampling valve is switched and the sample loop content is introduced into the GC application. This greatly improves the repeatability of a gas analyzer and in-between operator repeatability of the sample analysis. 13X is a crucial column that separates oxygen from nitrogen and methane from carbon monoxide. This column is like a sponge and it will capture and hold any moisture or dirt coming from the samples or the carrier gas itself. Due to this, the column separation will become poor, especially that between methane and carbon monoxide, as you can see in these chromatograms on the right. In the past, lab operators could regenerate this column by having to take this out of the GC application and mount it into another GC that can heat it to a much higher temperature. For the current high-speed RGA, we offer a programmable 13X which can condition this column while leaving it in place. By running a supplied conditioning method, the 13X column is conditioned in 4 hours time and the separation will be good as new. This is much simpler and prevents potential leaks from removing and reinstalling this GC column. Lastly, having a good and easy to use software package to help simplify the analysis of the GC application is of importance. PAC offers our new in-house made RGA NGA Excellence software with the high-speed RGA application. Why is a software package so important for gas analyzers? Surely you need a software package to identify and quantify all the components in the composition of a gas. This by itself can be done direct in a chromatography data system software like OpenLab, but this can be done more efficient and user-friendly, optimized for a refinery gas analyzer. Surely one needs to calibrate the analyzer, and one of the poor things in a general chromatography software is to keep trace of when a calibration was performed and which calibration was used to calculate the results of a sample, and that in case it is used, one cannot manipulate the calibration. Having a software available that takes care of that is of importance in case you get an audit. The software, of course, should be able to calculate the physical properties of a gas, like the calorific value, Wob index, specific gravity, etc. And in addition, that it is calculated by the desired method, at the metering conditions desired, and of course that it is reported in the unit desired, like megajoule per cubic meter or BTU per cubic feet. All of this adds value for the operation of the gas analyzer on the lab, but also literally for the gas analyzed. Knowing the energy content, calculated from the composition of a gas, has a monetized value. So let's have a look at a video of the RGA NGA Excellence software, how a sample analysis is performed. We are now looking at the import screen of the RGA NGA Excellence software on Iris. If you're familiar with Simulus Excellence and DHA Excellence, you will see that the input screen is identical to what you're familiar with. I have a result ready. I just need to start the automatic import. If you leave it on, it will always do that, and you will see in a very quick manner the file being picked up and processed. We are now in the Results tab of the RGA NGA Excellence software. On the left-hand side, you see the list of processed analysis, including the sample we've just processed. Simply double-click the analysis file to open it up. We now see the main screen where customers could work on for the sample analysis. Basically, there are two tabs, the Identification tab as well as the Calculation tab. In the Identification tab, it's all about checking the identification of your sample if all the components are correctly identified. In addition, you see some settings about how peaks are identified itself and the total unnormalized mole percent. Other than that, we can see a few other things that we can do here. We can look at individual chromatograms, and if necessary, we can change the naming if necessary, if we need to do that. If you corrected it, all you need to do is save it to the test, and we'll keep it for future analysis. If you need a reference chromatogram because you're not sure the identification is correct, you could take a sample analysis or a calibration analysis as a reference, and all you need to do is to click this button to show your reference chromatogram here portrayed in gray on top. To see the result of the actual analysis, we can see it in two places. Logically in the report, if you click that, but first we can review it in the Calculation tab. In the Calculation tab, we basically see the list of the components with the found percentages in the different units as required. As well, if you've made a group, like here I've made all the total olefins together is a report. As well, we see here on the right the different property calculations. For example, this ISO 6976 from 2016. In case you want to print the report, simply click on the print icon. It will load and set up the report as specified in the software. Here you basically see now the same result as in the Calculation tab as we've seen before. Surely this report can be further modified into the customer's liking. In the end, if the result is found correct by the customer, besides printing the report, we always still can transfer the results to a LIMS, which is included in the software. To highlight the main features of our new RGA NGA Excellence software, it is a workflow optimized software where every step in the software can be automated. Having a simplified user interface optimized for gas composition analysis, and being capable of measuring all kinds of known physical property calculations as per ASTM, GPA, and ISO methods at varying conditions. And for those that have other PSC instruments and software, all our software for DHA, SimDis, Reformalizer, and Elements share a similar look and feel, which is easier to train lab personnel. By this, I conclude the refinery gas section of today's presentation, and I'm pleased to hand over the presentation to my colleague, Basu.
Thank you very much, Rob. Hello, everyone. My name is Basudev Chakraborty. I'm the application specialist supporting the chromatography product line here at PSC for the Americas region. In this role, I interact with our customers on a regular basis. I try to understand their specific needs and provide them with an appropriate solution to meet their analytical requirements. A little background about me, how I started in this journey. I have always been fascinated by molecular structures and how chemical and physical properties of materials are influenced by them. This led me to pursue my bachelor's in chemistry and then further my master's degrees in applied chemistry and then with a specialization in inorganic chemistry. Before joining PSC, I worked at Dow Chemical Company and ExxonMobil as part of their analytical method development team, where I supported different manufacturing and business functions by developing and validating analytical methods for troubleshooting of process to qualification of final products. The topic we are going to discuss today in this segment relates to analysis of different hydrocarbon group types and oxygenates in gasoline. Reformulizer M4, developed by PSC, is an excellent analytical measurement technique based on multidimensional column switching and flow. This analyzer is capable of providing very accurate compositional analysis for gasoline and blending feedstocks. As we look at the analytical challenges in gasoline analysis, it really stems from the process by which we obtain gasoline from crude oil. In a petroleum refinery, crude oil is distilled and the various distillates are converted or upgraded if needed to produce valuable blend stocks for gasoline. The gasoline is then blended from these blend stocks, yielding a product with favorable properties at lowest possible costs. We know gasoline can contain various types of compounds like paraffins, naphthens, aromatics, in some cases olefins. Additionally, oxygenated components can be blended into the gasoline to improve combustion characteristics or meet environmental requirements or renewable content. Now in US markets, mainly ethanol is used as a blend stock for reformulated gasoline. In Europe and Asia, however, the diversity of oxygenated components in the gasoline pool is much broader. Components include alcohols such as methanol and ethanol, but also a significant amount of ethers are used, including methyl and ethyl tertiary butyl ethers. In some cases, heavier ethers such as tertiary amyl methyl and ethyl ethers are also added. The addition of these various types of oxygenase add to the complexity of analyzing gasoline, and so the technology chosen to analyze the gasoline for oxygenates should be able to detect and quantify these components without much interference. Traditionally, detailed hydrocarbon analysis, or DHA, is a technique used in petroleum industry to analyze composition of gasoline. We try to look at PONA components, paraffins, olefins, naphthens, and aromatics to get an idea about the overall quality of the sample. In this slide, we see the challenges associated with this technique. As you look at the concentration distribution of components present in a typical gasoline based on a DHA analysis, a total number of 221 components are detected, with concentrations ranging from below 50 ppm to higher than 10%. This is equivalent to a dynamic range of more than 3.6. In this graph, we see a long tail of components present in small concentrations. The possibility of occurrence of number of isomers in the higher carbon ranges for olefins and naphthens makes this analysis even more complex. This tells us that accurate analysis of gasoline requires proper separation of components and a highly sensitive and linear detector covering the full concentration range. Now, in addition to the previous slide, we see here a zoomed-in view of the chromatogram of the DHA analysis around the C9 region. You can clearly see that below the area reject, a lot of components elute, many with multiple coelutions. This has a few implications. First, the number of components present is far greater than the 221 detected components in the DHA analysis. Second, besides separating and identifying, sensitivity and linearity are of equal importance to the analytical method of choice. Enhanced detector linearity will allow accurate quantification of components present in high concentration while preventing disappearance of low-level components in the noise of the detector. And third, there is an additional advantage for group type separations. Due to the grouping of components in the chromatographic process, detectability of components is much improved. This will result in a more accurate determination of the hydrocarbon group types present in the sample. These challenges are overcome with help of a multidimensional GC application that we call Reformulizer. Here you can see the picture of Reformulizer. It is a pretty compact analyzer that can extract the complex gasoline mixtures, feedstocks, and oxygenates into each group types using simple and robust separation techniques. Aromatics and oxygenates by polarity, paraffins and naphthens by molecular size, and olefins by unique AC olefin trap. It is a globally accepted analytical method listed in various field specifications from ISO to ASTM. We have a dedicated procedure for ethanol E85 automotive fuel, and we also carry out a biannual global performance monitoring program to ensure reliability of method and data. Multidimensional chromatography may sound complex, but it is actually a simple technology where one uses multiple standard separation principles like boiling point, polarity, and molecular size in one system. From the flow diagram, you can see we have one inlet where the sample will flow in various directions after pre-separation and undergoes these multiple separation scenarios to be detected all by one single FID detector. It is a very straightforward process from sample introduction to data analysis. Here we can see how the sample is divided in the reformulizer to its maximum separation, the Opiona method. The sample is introduced into a pre-separation to non-aromatics, aromatics 1, and the second aromatics with alcohols. Where the two aromatic groups undergo a similar separation based on boiling point, the non-aromatics, however, undergoes several separation steps, taking out ethers by an ether alcohol trap, separating the saturates from olefins via olefin trap, and the saturates can also be further separated into iso and normal paraffin isomers by using columns that separate based on molecular size. The components are released at different times to release the FID detector at separate times, and that is how we obtain a fully resolved chromatogram of gasoline. The development of the reformulizer goes along with the development of refinery processes, starting with the alcohol separation to fluid catalytic cracking process relevant for olefins. So here you can see how different group types are separated in a typical gasoline sample when you run it on a reformulizer. In a gasoline mode or Opona mode, we can see each group types are clearly separated and identified. We have dedicated modes for different sample types, such as E85 mode to reformer feed mode for those type of samples. This takes the guesswork of changing method parameters for different sample types out of the equation and makes the analysis process smooth and reliable. This gasoline mode has been further improved in separation of alcohols and ethers with the introduction of the gasoline oxy mode, which takes only 52 minutes to run compared to 3 hours on a full DHA analysis. This mode has an improved separation of oxygenates, which is needed for when a more complex blend of oxygenates are blended into a finished gasoline. Our M4 reformulizer runs only on nitrogen and hydrogen as carrier gas, so we can avoid using expensive helium option. The reformulizer has an extensive sample scope, ranging from C4 to C11 hydrocarbons of different groups like paraffins and aromatics, and a wide variety of various ethers and alcohols. Since FID detector used in the reformulizer has long linear range, it can measure a broad concentration range from smallest concentrations up to high percentage level, covering all gasolines and the feedstocks that can be blended in a gasoline. The new M4 reformulizer can measure up to 75% of olefins and 95% ethanol in our samples. As mentioned before, we have set methods for different sample streams starting from FCC naphtha to reformate to an E85 blend of gasoline. The reformulizer software is very workflow oriented and intuitive to use. Starting an analysis is just a few clicks. Once the analysis is finished, the report is generated automatically. On a routine basis, the operator only has to check whether the group times are still in right place. Should one have to correct group times, then changes are immediately visible in result table. Now let's have a look how to start a reference analysis in the Reformulizer M4 software and how to adjust peak identification if necessary. This adjustment is not expected in daily use as methods are optimized for sample types. By clicking on the Add button, we can add an analysis to the work list. Simply add the sample name, file position, choose the sample type, if it is a QC or an unknown sample, and choose which mode of analysis you want to use. In this example, we choose gasoline mode and select our QC gasoline M. By hitting on Save, the analysis is added to the work list. Once completed, we can review the analysis in the Results tab. Double-click on the analysis to open. You can directly see the results displayed below, and if any corrections are needed, for example aromatics 8, simply zoom in and move the group time. Results are automatically updated. If corrections are made, hit Save. Here we see an example of a report that can be automatically generated at the end of the analysis. This report is customizable, again, method and product dependent. What is selected in this report is the ISO 22854 summary, a list of individual oxygenates and group type by carbon number table, both volume and mass percent. So what we see ultimately is that the reformulizer is a direct measurement method with true separation, no concerns on linearity, and quantification is done on theoretical response factor and normalization. Now, to add to the versatility of reformulizer, we have M4 prefrac. This is a full standard M4 reformulizer with an additional pre-fractionation inlet. Just like the regular M4, it gives us a group type analysis up to C12. With this option, we have the ability to introduce a sample with final boiling point up to 525 degrees centigrade or 954 degrees Fahrenheit. The sample stream first goes through a pre-fractionator liner where the heavier end of the sample is back-flushed to vent and the lighter end of the sample elutes to split inlet to go through the full process of reformulizer. This option provides tremendous advantage when it comes to accurate compositional analysis of heavier samples such as pyrolysis oil. To summarize, with Reformulizer M4, we need only one analysis for the full composition using a combination of basic simple chromatographic principles. Instead of using multiple methods For different groups and different concentration ranges, we can measure from high to low concentrations, performing one single analysis that takes about 40 minutes. In this case, we are working with simple and robust flame ionization detector with easy theoretical response factors for which no calibration or detector tuning is needed. This makes identification and quantification easy. The main user interface is its easy-to-use, workflow-oriented software with automatic report generation and LIMS export functionality. We also have Reformulizer diagnostic tool and dedicated AC calibration and quality control samples for system performance validation. This makes M4 Reformulizer the perfect candidate for accurate compositional analysis for samples in gasoline boiling point range.